Today we're going to be starting to look at capacitors. So, capacitors began to be, the phenomenon of capacitance began to be discovered in the 1700s with the discovery of something called a Leyden jar. And this was a jar which had either water in it or alcohol. There's a cork. There's a bit metal here that goes down into this liquid. And it was discovered if you were to, here's our man. It's just, he's too far away from our Leyden jar. So he touches the Leyden jar. And this is going to be charged by some device that charges it, and the electrons are coming down here, down to here, and then they pass to the side of the glass jar. But glass is an insulator, and it can't get through. But what can happen if you think? So I'm going to draw. This is the surface of the glass, and here we've got electrons piling up. And this is the guy's hand. Just a finger here. But so what happens here is electrons in this hand, they go that way. And so you get positive charge building up here. And so you've got this positive charge building up on the hand of the person and negative charge here. Now what happens if this guy then touches the metal here? The whole thing discharges and he gets an electric shock. And this phenomenon was something that scientists in the 1700s found completely and utterly baffling. They just couldn't understand what was going on here. Because they didn't really understand the nature of electricity. They thought electricity was a type of liquid, that's why they put it in water or alcohol. And they discovered this by trying to find a way of storing electricity. And they thought, well, we store water in a jar, so we'll store electricity in a jar. But they missed the fundamentals of what was going on. So this little setup had no real practical usage. It was just used for entertaining people and giving people electric shocks at parties and such like. And people made a living from doing this to other people. And it was great fun. But pretty useless for practical uses. Let's move on in time, and we now use this setup in capacitors. And capacitors are a vitally important piece of circuitry that we use in pretty much everything. So we have two metal plates, and here's our battery. And we have our positive side of our battery and we have our negative side of our battery. And what this positive side of the battery does, this strips electrons off this plate, so they come through here and they get pumped through the battery and then they pile up here. Now because this plate here has lost its electrons, this is then positively charged. And what we have set up is, let me just draw, so you've got your positive plate, oops, and your negative plate. So we have an electric charge, an electric field, sorry, between the plates of our capacitor. And this is a way of storing charge. We have, typically, the plates will be, you'll have a metal plate here, two metal plates, here and here, and let me just get a different colour. In the middle, you'll have some type of material, some kind of insulator, but it can't just be any insulator. So this here is what we call a dielectric material. And so a dielectric material is an insulator. So it's stopping the electrons from closing the gap and coming back here, because they really want to come back here. They want to close this gap. These electrons don't want to be there. They want this to be closed. They want to go back to where this is positive. But because it's an insulator, they're unable to close the gap. So it's an insulator, but it has to be one that can sustain an electric field. And typically these will be things like paper, ceramic, glass. These are all really good dielectric materials. Now, if you were to see, if you look at some pictures of what capacitors look like, modern day capacitors look like, they're often little sphere things with connectors coming out of them, or little circular discs like this, or little flat things like that. So how does that, something that's two plates with a dielectric material, actually get into something like this? So because the things that so let's take a step back. What makes a good capacitor, i.e. can store lots of charge? One is the dielectric material, and two is the surface area. So if you want to increase your capacitance, you need a big surface area. So what happens is you'll get two. I'm going to colour, actually, let's do this gold and gold. This is meant to be gold. This is a sheet of gold. And then you get another sheet of gold. And then in the middle, we'll put some diametric material in the middle here, between them. Let's just colour that bit in there, gold. So you've got your two metals, two sheets of metal, and then what they do is they roll this up like a Swiss roll. So they roll thin metal sheets with the dielectric material in between, into a Swiss rolls type shape. And then you can put your, so you then end up with a coil, coiled up like that, and you can shove it inside this. And that's how they can make capacitors fit inside, have a large surface area but fit inside a small a small device. Capacitors are found in computers. They are tuning devices. Like radios, TVs. Massive capacitors are in lasers, in industrial scale. And they're really important. You'd struggle to find a circuit in your electrical gadgetry that doesn't have capacitors in it. They're just absolutely vital. So let's clear this. So every capacitor has a capacitance. In other words, the maximum charge it can hold. And that's what we were talking about. It depends on the surface area and the dielectric material that we use. And the plates also need to be close together to store that charge. So the amount of electrical energy and so charge, which can be stored in a capacitor, directly depends on the potential difference across it. So let's draw a little circuit. That's meant to be a battery, not a capacitor. Oh, dear me. There we go. Here's our capacitor. And what we're going to do is we're going to have your supply potential difference in volts and the maximum charge in the capacitor. And we'll measure that in microcoulombs. So say we start off with a voltage of 1 volt. The capacitance is going to be 5 microcoulombs. Say we then do 2 volts, this will go up to 10. This 3 volts will go up to 15. 5 volts, oops, 4 volts. 4 volts will go up to 20, and 5 will go up to 25. You'll see already we've got a nice linear relationship. So if we were to plot this out, so you've got supply potential difference over against the charge, and we're in microcoulombs, what we get is a straight line curve through the origin. Now the gradient is equal to 5 times 10 to the minus 6. Now the gradient will be the units, of this gradient we can work out. This is a measure of how many coulombs of charge we're able to create from 1 volt of potential across the capacitance. So this is how many coulombs charge we have per 1 volt potential across the capacitor. So in other words, we've got charge per volts. Now this is the units of this gradient, and we call it farads. Farads is and its symbol is F. Farads is what we measure capacitance in. So 1 farad is equivalent to 1 coulomb per volt. This is in fact a massive capacitance, and we don't really get 1 farad capacitors. Capacitors tend to be, they tend to be pictofarads, sorry, or in the microfarads, even nanofarads. This here is 5 microfarads, and that's a pretty typical size for a capacitor. Now this leads us to the mathematical relationship between charge, capacitance and potential difference. So charge is equal to capacitance times voltage, or capacitance is equal to charge over voltage, where charge is measured in coulombs. I can't spell coulombs. Coulombs. I was right. Capacitance is measured in farads. So that's F, this is C, and this is obviously volts. Just be careful that, because charge is measured in coulombs, which is C, but capacitance is different, and that's farads. Just be careful not getting your C's muddled up. The farad is named after Michael Faraday. Just for your information. So you need to note that this relationship has a limit. If the potential across the capacitor is too high, the electric field will break down. In some cases, there might even be a little explosion. Now let's look again at this relationship between voltage and charge, but this time we're going to have our potential difference here and our charge here. Now we're going to have our Vmax. So we just said that there's that limit. Now let's think about our capacitor. And let's think about if we have a voltmeter here measuring the potential difference. What's going to happen is the voltage will rise over time. It's not just going to suddenly, and when it's fully charged, the voltage, say this was 6 volts, the voltage here and the voltage here will read the same once the capacitor is fully charged. So we have this, as the charge increases, the potential difference increases, and it reaches this maximum level, and then we have the charge in our capacitor. And then we have this halfway, we're going to have an average potential difference in over the capacitor. Now, we know that the work done, or energy transfer, is equal to the charge times the average potential difference. So we've got, this is our energy transfer, electrical work done. Shifting those charges is equal to the charge, the amount of charge, times V, where V is the average potential difference. Now this means that if you look at the area under this graph, let me get a different colour. Let's just colour this in. To calculate the total energy transferred is equal to the area under the graph. But this is a triangle, so we can use our equation for the area of a triangle is half the base times the height, and that leads us to a series of equations for the energy transfer is half Q V max. So now we're using this maximum voltage, and so we'll just write that as energy is half Q V. Now we know from these equations up here, we can then rewrite the energy is equal to half CV squared. We'll write the full, so the full family of energy equations are half QV is equal to half CV squared is equal to a half Q squared over C. So this is the energy transferred in a capacitor and the relationships between them. So let's look at a problem involving capacitance. A circuit is created with 20 nanofarads capacitor and a 1 kilo ohm resistor in series with a 12 volt supply. What is the maximum charge which can be stored, and how much energy is the capacitor storing when Q is at its highest? So we know that charge is equal to capacitance times velocity, and the capacitance is 20 times 10 to the minus 9, minus 9 is nano, times the 12 volts. So that's going to give us 240 nanocoulombs. And we know that energy is equal to half CV squared. We can use this, we'll just use this equation. So it's half times capacitance, which is 20 times 10 to the minus 9 times the voltage squared, 12 squared, and that's going to give us 10 times 10 to the minus oh, I'm not going to write all that extra working down. That's going to give us 1.44 microjoules of energy. So I hope that helps.